Chapter 10, Modern Atomic Theory and the Periodic Table. And here we see pictures of fireworks. And in this chapter we're going to learn that fireworks, the colors, actually occur from electron-electron transfers between electron orbitals in the atoms themselves. So, electromagnetic radiation. This is a form of energy that is light energy. It runs down a continuum from gamma rays to X-rays to ultraviolet to visible light to infrared to microwaves to radio waves. Each form of radiation shares common characteristics. They display wave-like properties and travel at the same speed, the speed of light, in a vacuum. The basic properties of a wave, they have a wavelength. This is the distance from peak to peak or trough to trough. And the frequency, hertz, the number of times a wave passes through a certain point in space per second. And speed is how fast a wave is moving. So here we see the wavelength, the distance between two different peaks or two different troughs in a wave. And here we see the different portions of the electromagnetic spectrum. The most dangerous are gamma rays. This is just pure radiation. Gamma rays come from decomposing nuclei. Then we have X-rays, ultraviolet, visible. This is the portion of the spectrum your eyeballs can see. Infrared is heat. Microwave is what your microwave uses to make food warmer. And radio waves, which is what communications equipment uses. Just like matter, energy is also quantized. Just like matter comes in discrete units we call atoms, energy comes in discrete units that we call photons. And so it's like a particle of energy. A photon is a discrete basic unit of energy. And just like you either have an atom or you don't have an atom, you either have a photon or you don't have a photon. At high temperatures, or when high voltages are applied, elements will emit colored light, and only at specific frequencies. So here we have the line spectrum of hydrogen, and it shows the different frequencies of light exactly that light will be emitted. And Bohr studied these, and he realized that these frequencies of light being emitted were coming from specific electron-electron transfers, electrons moving from one electronic orbital to another electronic orbital as it's moving around the nucleus. When electrons absorb energy, they move further away from the nucleus. When they release energy, they release light in different frequencies, some of it in the visible spectrum that you can see, and they move closer to the nucleus. Every element possesses a unique and characteristic line spectrum. If you take general chemistry, you'll go through mathematical models on the exact mathematical equation that predicts every single possible frequency of light that could be emitted in the hydrogen atom. Here we see a model here that Bohr came up with, and when electrons gained energy, they'd move away from the nucleus. When they released energy, depending on what orbit they started with and what orbit they ended in, that would determine the frequency or wavelength of light that was emitted, and that would make up the line spectrum. So when an electron is at its base level, we call that ground state. Any electron that has more energy than ground state is called excited state, and there are multiple excited states. So the ground state is the lowest energy level for an atom. Each line of the line spectrum corresponds to an emission of energy from an electron as it moves from higher to lower energy. And again, the color of light emitted depends on the gap between the energy levels. And it doesn't have to be just visible light. For example, ultraviolet light can be given off, infrared can be given off. And so the light is in all sorts of wavelengths and frequencies. We just see the visible light on the line spectrum because those are the only frequencies and wavelengths of light that the naked human eye can see. Bohr's theory worked well for hydrogen, and it also worked well for helium +1 and lithium +2. And what all three of those specimens have in common is they have only one electron. As soon as you have a second electron, the math breaks down because the electrons interfere with each other in extremely complicated ways in which we cannot model with a computer yet. Because again, electrons are only 50% particle-ish. They're also 50% wave-ish. And that quantum duality is amazingly difficult to model. And so even today, our supercomputers cannot deal with those types of chemical or those types of mathematical equations. And so while Bohr's mathematical formula works amazingly well in a one-electron system, it doesn't work at all when you have more than one electron. Later, in 1924, de Broglie, a French chemist, proposed that matter, just like energy, could also be treated as both wave and particle-like simultaneously, which was an important part of the emerging quantum mechanics theories. There were a lot of questions about light, because light sometimes acts like a particle, like it leaves the sun and moves through the vacuum of space and comes to Earth, but it also refracts and diffracts like a wave does. And so light has both particle and wave-like properties. And they finally realized, after arguing about it, that light was both particle-ish and wave-ish simultaneously. And then de Broglie pushed that theory further and realized that matter was also wave-like and particle-like. The bigger object is, the more particle-like it is, and the less wave-like it is. And so, if something is big enough for you to see, it almost completely acts like a particle. An electron is at the 50-50 line. An electron is 50% particle-ish, 50% wave-ish. And then things smaller than an electron behave mostly wave-like. Schrödinger expanded on this in 1926 and came up with mathematical wave functions that describe electrons as wave. And so this theory of quantum mechanics allows one to calculate the probability of finding an electron in space. Quantum mechanics is an interesting theory. Everything is in probabilities. And it was extremely useful. There's a lot of things in chemistry that can't really be described accurately in any way besides with quantum theory. And so quantum mechanics is not very intuitive at all. There's no way to easily explain it to someone. They have to just understand the math. In this class, we just introduced the concept of it. We don't really go into it. So orbits, electron orbits, were replaced by orbitals, which are regions of space with a high probability of finding an electron. Inside of an orbital, there is a 90% chance of finding the electron. So the hydrogen atom, there's a 90% chance that it's in here somewhere. There's a 10% chance that it's somewhere else. I mean, it could be in Kentucky, but there's a 90% chance that it's inside here. And quantum mechanics is built up of all these different probabilities. Bohr's idea of quantized energy levels had parallels in quantum mechanics. For example, quantum mechanics predicts discrete quantized principal energy levels for electrons in an atom. So the principal energy level, this is your base energy level, and it can be 1, 2, 3, 4, 5, 6, 7. It's just 1 or greater, and it's always a small whole number, and it tells you which energy shell you're in with electrons. So your principal energy level determines your energy shell. Your sublevel determines the shape of the orbital. So we're going to have S, P, D, and F orbitals. S orbitals are spherical, like this one. And again, an orbital is a space that has a 90% probability of finding the electron in that space. Electron spin is represented by up and down arrows because this comes to the angular momentum. When you spin an object like a wheel, you create a new force. And so let's say I have a bicycle wheel. If it's not spinning, there is no force. But the second it starts spinning, you create a new force. And use the right hand rule, because if it's spinning like your hand is, your thumb tells you the direction of the force. If it's spinning the other way, if this is spinning this way, force is down. And so the upspin and the downspin mimic the angular momentum that you find in an electron. And that's why it's called spin, because back in the day when it was named, an object had to be spinning to produce this type of force of angular momentum. These days we know electrons are not spinning. They just happen to have this force. It is an intrinsic property of an electron. But they've already been named upspin and downspin, so we keep using the name. You can have two electrons in an orbital, but they must have opposite spins. That's a Pauli exclusion principle. You can never, ever, ever, ever have two electrons of the same spin in the same orbital. It is quantumly forbidden.